Okay.
Good day from the Radiant Professionals Alliance, and welcome to Hydronics Talk, a presentation of the Radiant Professionals Alliance. I'm your host, Mark Etherton, the Executive Director of the RPA. I've been a member for the last 20 years. I'm also a contributing editor to Contractor Magazine, along with 4 or 5 other magazines. Been an educator for 39 years, former expert witness, and still a current licensed master plumber here in the state of Colorado. Quickly go over some rules of the road. If you would please use headphones with a boom mic if possible, so that if we do decide to enable your mic to speak, that we don't get a lot of feedback. If you have a question that you would like me to ask our guest, type it into the Q&A box, and I will interrupt him when it's convenient and have him answer the question. And then questions regarding the presentation may be responded to after the presentation if you would like. I'd like to thank everybody for their time and attention in attending. Here's an example of an early alternate radiant panel system that I helped put into a Habitat for Humanity house about 20 years ago. Big fan of alternative radiant heating systems. There's the radiant ceiling system under construction in my house up in the mountains. And I've got a couple of layers of 5/8 sheetrock on there that's tied to a solar panel. So I basically have my storage system in my ceiling. Free heat. Here's the only advertisement you'll see during this show. We would love for you to join the Radiant Professionals Alliance. If you go to radiantprofessionalsalliance.org, there is a join button there that you can click on, and it will get fixed up with the information. It's very inexpensive to become a member. Tell you a little bit about the talk show. We have monthly guests that we bring in that are related to the hydronics industry in one capacity or another, and interview them with the different products that they have. Then we have an open Q&A session following the interview that doesn't have to pertain to the actual presentation. So if you've got a problem and you would like to have us address it with our panel of experts, by all means, feel free to bring it to the floor and we will address it as well as we possibly can. These shows are archived for members only, review at a later date. If you're not a member of the RPA, this is the only time that you'll be able to see it until you become a member. Once you are a member, then you can go in at your leisure and review all of the shows that we've got, and man, we've got a lot up there. I think we've got about close to 2.5 years worth of shows that we've accumulated on the website up there. The shows are meant to be fun, educational, and entertaining. If you have someone that you would like to submit as a guest interviewee, by all means, send them to me at mark.etherton@iapmo.org. Quickly go through some hydronic news that you can use. The ASSE Standard 19210 hydronic certification training is now available for manufacturers reps, and qualified wholesalers. If you know somebody that might be interested in having me come up and put on the 3-day presentation, by all means, have them contact me at mark.etherton@radiantpros.org, and we'll fit them into the schedule. Taco HVAC Solutions is holding their advanced soup to variable speed nuts with John Barba, October 20th and 21st, and that will be at the factory up in Rhode Island. The AHR Expo is coming up January 30th, 31st, and February 1st. It's in Las Vegas this year. For more information, you can click on the live link of ahrexpo.com and see what's all going on. We've got 5 different classes that we'll be presenting this year with a very large group of subject matter experts. And the Radiant Professional Association's annual meeting and educational program will also be in conjunction with the 2017 AHR. I just noticed I've got a typo there. So stay tuned for more information on that. We're already starting to send out information via email on that. The RPA University fall courses are available, up and running. And there's some live links to the different classes that we've got there. And we're working on more classes as we speak. The graphics and illustrations used in this webinar are presented for educational purposes only. RPA-IAPMO does not endorse or recommend the vendor, product depicted, nor any vendor or product. RPA-IAPMO makes no representation, warranties, or guarantees as to, and assumes no responsibility for the products depicted, and RPA-IAPMO expressly disclaims all liability for damages of any kind arising out of the use or performance of the vendor's products or services depicted. And that's a mouthful. Today's guest is Bob Rohr. Bob Hot Rod Rohr, as everybody in the industry knows him, has been around for about as long as I have in this industry. And Bob, welcome.
Yeah, thanks.
You are now driver in control.
All right. Well, thanks everybody for tuning in today, and we'll talk a little bit about water quality, fluid quality, really. Anything that happens to be inside your hydronic systems or in your solar systems or in your geo systems. I mean, anything that uses, a fluid or water as a conductor for the heat falls under this category of water quality. So, and why this is becoming more important as of late is because a lot of the high efficiency boilers are a lot more sensitive to water quality than some of the the older cast iron blocks that were used to. They're quarter-inch thick. They held 40 gallons of water maybe, and I mean you couldn't destroy the darn things. But now we're looking at heat exchangers that are maybe a gallon and a half of fluid quantity, I should say, and a couple thousandths of an inch of metal on there. So we don't have a lot of wiggle room as far as wear surfaces in a boiler like that. So the other thing is, if you're going to sell your customer a high efficiency boiler and you put crappy water in and then you start scaling off the surfaces of the heat exchanger, you don't have a high efficiency boiler anymore. In fact, it only takes a few thousandths of an inch of buildup of lime or scale inside those tubes of that boiler, and the efficiency drops quickly. I've got some charts I think coming up that show, how quickly that drops when you start coating out the heat exchangers. Think about when you pull an element out of the bottom of an electric water heater, and you see all that buildup on the element, and eventually the element burns out because it can't get rid of its heat because of the coating of the minerals that are built up on it. Well, the same thing's happening inside your boiler. So we'll look at what's in the water, what you can do about it, and why it's so important. So at Caleffi, we did an hydronics issue on this, I guess not too long ago, about 6 months ago, issue number 18. We tried to keep it fairly short, and small. It's about 30 pages in there, because what you'll find when you start learning about water, because I didn't know a lot about water quality. I mean, I knew about water softeners from my plumbing days and, reverse osmosis and some of the different devices we had put in. But I'll tell you, when you start getting in the water, it gets pretty deep pretty quick. Not physically deep, but the topics and you pretty much need to be a chemist to start understanding some of the lingo when you get into it that deep. So we said, well, we can't go out there with that kind of message. And number one, we have to find somebody that can explain that. And number two, we don't want people to just ignore this and say, well, that's way too complicated. I'm just going to do what I've been doing. It's been working for me. So we tried to boil it down to a pretty understandable level. We found some people that are experts in the industry that could explain what we need to do for a boiler that's different than drinking water, different than pharmaceutical water, for example. So we'll talk about all the different things that can be wrong with water, the physical and chemical characteristics of water, what salts are and how the salts form in the minerals and stuff like that, and the difference between softened water and demineralized or deionized water, and of course the cart that we've got that can clean up the water and how you can test it and what you can do about it. So got a lot to cover, but I think we can do it. So there's a couple things about water, the physical quality of water. So when we talk about the physical quality, those are all the things that you can, I'd like to say, see or hear. So it's like air that's mixed in there. If your system's making gurgling noise and sounds like that, you've got air in, and that's usually pretty easy to handle with a good purge or a good air elimination device. We can handle that pretty easily. That hasn't been much of an issue since we've had the micro bubbles resorber type of purges like you see in the picture there on the market. That's as long as it's going through that device, you're going to get the air out of it, even the micro bubbles. And the same thing with dirt. Over the years, we've had Y strainers or cartridge filters or pot feeders. We've had different types of devices that can, handle the dirt that's in the water, the, particles, rust or scale or stuff like that. And now we've got devices that go on some of the dirt separators that will take any small magnetic particles. So I'm talking about particles that are microscopic, actually, that you couldn't get them out with any kind of strainer or filter. They're like 5 micron or smaller, which 5 micron is an example. If you pull a hair out of your head right now, that's about a 5 micron size. So you can imagine stuff that's under a 5 micron. There's no way you would ever filter that out with a cartridge or Y strainer. It would plug up almost instantly. So that's the type of particle that we can get with a magnet because it's not sensitive to the size of the particle. Now, there is one other thing about water, and it's the bacteria, microbial corrosion or biobs that's in the water. And an example of that would probably be like Legionella in drinking water. That would be an issue. In a heating system, there's iron bacteria. There's different types of bacteria that can actually get in a system. Now, they have to come from somewhere, and they have to survive inside a system, they need a food source. And typically, a food source in a hydronic system would be any solder flux that's left over there, cutting oils, any of the assembly lubes. Actually, when they draw copper, there's a little bit of lubrication that they use when they draw the mandrel through to make the tubing. And some of that fluid gets left over in there, and that could be a source for bacteria. I've only seen it once in my lifetime in my career in the hydronics, where we had a bacteria issue where we had to get some experts in there and identify it and then come up with a solution for that. But that is a possibility. We're not going to talk much about that because it is such a rare thing. But if you get to a job and you can't figure out what's going on, it could be, you've got a bug in there that's eating away your components. And it looks not unlike this picture up here. It'll actually start dissolving the soft metals in there, like the cast iron or the steel nipples. It actually just starts eating them away like you had a sandblaster inside there.
Bacteria loves glycol, by the way.
Yeah, well, that's a food source. That's a petroleum-based product. Glycol, it comes from a barrel of crude oil, or now you can get it from bioproducts like corn or from soybeans are making glycol, but that's the food source. So, yeah, bacteria would like to live in a system with that, and it's even sweet tasting. So, but so mainly what we're going to focus on then, knowing that we can handle the dirt and the water pretty well with different types of separators, is the chemical part of the water. So these would be all the different minerals that are in water. And if you think about it, water really is the universal solvent. So wherever your water is coming from, whatever type of rock or aquifer, lake or stream or well or spring, wherever it's coming from, that's what's going to be in the water, what's in the ground where that water is running through. And it was interesting because this spring, Ellen and Max and I took a hike down into the Grand Canyon, and it's about when I was doing research for all this water quality stuff. And as you walk down in the canyon, you see all these layers. It's almost like a sandwich. You'll see like red rock, you see, which is iron. You see the black, which is the sulfur. You see the white, the calcium, and the lime. And every couple hundred feet that you hike down in there, you see a different strata level, just like somebody had taken a line and draw it across there. So I'm thinking, well, wherever your well was drilled into and wherever it ended, that aquifer is what would be in the water. So if you got red water coming out, you've got high iron in it. If you got stinky, smelly, kind of dark water, it could be sulfur water. So, and that can change. If you've got a well that's, let's say, 300 feet and your water table's up 150 feet, on a dry summer when they're pumping the well a lot, you could be down into a different water level completely by the end of the summer. So, you test your water one day and you could come back 6 months later and have a complete test on that water because of where it's running through the different aquifers. So, but when we look at that, we look at the minerals that are in there. And one of the problems with the minerals in there is they make the water more conductive. And the more conductive the water is, the more you can have electrolysis where you have dissimilar metals in there, because you need an electrolyte for two metals to react with one another. You need the dissimilar metals, but you also need the electrolyte, which is the minerals in the water. So if you could strip everything out of the water, it wouldn't have conduction and you wouldn't have electrolysis in water. I'll show you what happens is, when you put like copper and galvanized together, those two wouldn't react with one another unless you had the electrolyte in there that had the minerals, had the high conductivity. Now, if you think about that, we've been putting copper, fittings in the cast iron boilers for years, and unless you had a leak in there, that's not a problem with corrosion. But as soon as you put copper into a galvanized nipple on a water heater where it's getting fresh oxygenated water every day and new minerals coming in every day, that's when you'll see electrolysis, and we got to put some break in between them. But inside a heating system, really all we need to do is get rid of that problem in the original water. As long as you don't have a leak taking on water every day, you won't be having that problem. And then we got to get the dissolved oxygen out of the water. So here's what happens when you fill up a hydronic system for the very first time. It could be a brand new system. It could be a retrofit boiler. So you put water in there, and the water that you put in there, H2O, has oxygen in it. The air we breathe, whatever air is left in there that you didn't purge out until you get all the little bubbles to come around, the air we breathe is 78% nitrogen, 21% oxygen. So there's not a lot of oxygen in a system from the air that's in there or from the water that's coming in there. In fact, Amtrol did a study a couple of years ago. It's in their engineering guide, and they tested water in 5 different cities around, probably around Rhode Island where they are there, and they found that less than 2% oxygen in the water. So there's not a lot of oxygen in the water. And so what happens with that oxygen that's in there, that either comes in with the water that's left from the air that you didn't purge out of there, usually within the first couple of days, the first week that that system is running, all that oxygen will oxidize any metal component that's in there. Now, it's going to be, the body of your pump, if you're using cast iron body pumps, if you use steel nipples to, screw into the boiler, your expansion tank. So if you took that system apart a week after you got it running, you would see like a red or blackish coating on the inside of all that, and that's the oxidation that was caused by the oxygen that was in there. So once that oxygen gets consumed or used up by that oxidation process, you've got what's called dead water or oxygen-starved water. And there can be no further corrosion in that system unless more oxygen gets in there. So when you see a pump that looks like that when you take it out, that's had oxygen getting in there. There's no way that that sludge or that rust could form unless there was oxygen, because things just don't rust. Think about when you look at how they store antique cars now. They put them in these big plastic bags, and they suck all the air, suck all the oxygen out of there, and there's no corrosion. Those cars will just stay like that for years unless that bag leaks air into it. Or, when you buy milk in a plastic container, excuse me, there's an EVOH liner inside that plastic container, and that's in there to keep the oxygen from getting into there, which will spoil the product after time. So they're called internal coatings. But and the same thing with PEX tubing. Somewhere on that PEX tubing, if it's made for radiant, for hydronic use, there'll be some kind of barrier. It might be an EVOH barrier inside of it or outside it. It might be aluminum layer on it. Some way they're trying to keep that oxygen from getting in there, because this will keep happening if oxygen keeps getting in there. So we got to get that out, and we got to keep it out. And then galvanic corrosion, again, for this to happen, where that steel or whatever type of nipple is screwed in that brass valve, you've got to have an electrolyte in there. You've got to have conductive water, or you won't have this happening. So all these things here in these pictures we can fix by just demineralizing or deionizing the water. So let's look at a couple different ways we could do that. And I must have 25 of these pictures now that have been sent to me by different manufacturers or wholesalers of boilers that have come back that have failed. This is a fire tube type of boiler, and you can see all the buildup of scale and stuff in that boiler. Obviously, that keeps the flame from getting down to the fire tubes and transferring the heat down into the water we want it. So this isn't the fault of the boiler. When they get one of these back and they take a plasma cutter and cut them open like you see here, that's not going to be warranted any longer. In fact, our rep out in the west in Utah there, he said he had the brand that he handles. He said they had 142 warranty claims on the boilers last year from different issues, and he said 84 of them were refused. He said that's the first time ever that they started refusing warranties, at least that many of them. And they're saying, it's not our fault anymore. If these boilers are failing because of water quality, we can't keep giving you new heat exchangers. This is, they're going to raise the price of the boiler if you keep doing that, because somebody's going to have to pay for that. So this is, I think once one boiler manufacturer takes and draws that line in the sand and said, listen, no more warranties if the boiler comes back looking like this, or they do an analysis of the water when they get it back to the wholesaler there, they're not going to warranty that. So I think other manufacturers will fall in line and say, well, listen, that brand isn't doing it, we're not going to do it anymore either. So we got to figure out what we can do to prevent that from happening, and it's not that hard of a thing to do. So,
Bob, I got a question for you on that picture.
Oh, okay.
That line scale looks like it's in the combustion chamber.
Yeah, it's up above there, and I don't know if that was from the condensate or whatever, but yeah, typically the burner on this type of heat exchanger is up above there, so that's coming out of yeah, you can see it. It's up in here.
Yeah.
Where that picture's showing.
Like maybe there was a leak in the combustion chamber then.
Could be, but again, it failed, and it wasn't. It wasn't the fault of the boiler, obviously.
Well, yeah, it's obvious.
So the main thing that we want to look at is the hardness of the water. So usually when we talk about hardness that we measure like with a water softener test kit, where you put the drops in there, you count how many drops and you shake it and say, okay, it's so many grains or parts per million hard. That's usually looking at the calcium and the magnesium and the lines and stuff, and those ions in the water. And the more stuff that's in your water, the more of these minerals that are in there, the higher the electrical conductivity of that water. So there's different ways that we refer to that. Sometimes it's called grains per gallon, GPG. So 1 grain is equal to that. If you weight it, that's what it would weigh in a weight. The other number that we look at is parts per million. And typically when we talk about TDS, total dissolved solids, we talk about parts per million. It can be looked at as microsiemens. There's other indicators of that, but The most common way that we talk about it here in the U.S. is parts per million. So 1 grain up here would be the same as 17.1 parts per million. So if you got a number from your test kit that's in grains and you want to turn it into parts per million, there's the multiplier that you would use for it. So this is a pretty vague map. I know our rep up in Maine also does water treatment, and he says, you know, I can go to different parts of Maine, either along the coast or inland, and see quite a bit difference in the water, the hardness of the water. So he said this map is pretty deceiving. You think, well, they got pretty good water up in Maine. He said, no, it really depends what part of Maine that you go to. And certain areas surprised me. I was up in Long Island here a couple months ago, and I take my TDS meter with me now, and everywhere I go, I just get a cup of water from the faucet in the kitchen or wherever I am, and I test the water. And I found the water in 3 different places that I went on Long Island was actually pretty low TDS, which surprised me. I thought that water came maybe out of the Adirondacks and would have had a lot of minerals in it, but for some reason, this map actually was pretty realistic for Long Island anyways, that they had relatively soft water. So, but again, that water could change. I could go back there at a different time of the year, maybe on a dry summer when all the golf courses were pumping real hard and watering, and that could be a different picture altogether. So when we talk about the stuff that's in water, salts is kind of the term that they use to describe everything there. So those are minerals that have been dissolved in the water, and they're referred to as salts. And that can be some of these you recognize in the picture here, maybe from your chemistry on these bubbles here. I mean, you got chlorides in the water, you've got sodium bicarbonate in there, you've got the magnesium in there, the Mg, wherever that one went. So there's all these different things that can be in there. Now, some of these are called cations. The ones that have positive charges are called cations, like these here, and the negative ones are called anions. Now, what happens is when we go to treat this water, we want to strip these things out of the water. So one of the first things that we can do, the simplest thing to do, is just run it through a water softener. And so basically what a water softener will do is it'll take part of these out. It'll take I got to remember it's the negatives, the positives, because what they do when they build the water softener, the resin that they put in there, those little brown Z-like beads that they put in there, they put a charge on those beads. They chemically etch those beads to a charge so that it'll track the opposite to those beads. And then once the beads get filled up or plugged up or attached with all the hardness, the minerals in there, you backwash it by putting a brine solution in there that's the opposite charge, and it's an ion exchange. So you exchange these bad things in the picture for the salt, the brine that's in the tank. So maybe a good way of saying that, you take the bad stuff out and you put less bad stuff in there, because when you do the ion exchange, you still end up with water that has a real high conductivity. So it's still got the potential to do some corrosion. It certainly has the potential to do support electrolysis, because it's almost like, it's like when they build a battery for your truck. If you go out there tonight and dump all the acid out of your battery and you come out tomorrow, you're probably not going to be able to start your truck because the electrolyte is gone. Well, the same thing. If you take some of this out but put sodium back into it, you still have an electrolyte in there. You still have conductivity in your water, and you're still going to have some of these issues. So what I want to do is get everything that's in this picture, all these things here that could be in there. I want to get everything that's in there. Now, it's hard to make perfectly pure water unless you're doing it for pharmaceuticals or something like that. And we don't really need it that pure for boilers. We just want to get most of the bad stuff out of there that's going to scale out our system. So now what we know about the different scales, the common salts that are in our water systems, is some of them become more soluble as the water temperature increases, and some become less soluble. So if you think of, I remember growing up, if I'd spray my ankle or something, my mother would get some warm water and she'd put Epsom salt in there, and that Epsom salt would just dissolve almost instantly, and you get this cloudy water, and you soak your foot in there. It's supposed to make the swelling go down or whatever. So that's an example of a salt that becomes more soluble as you raise the water temperature. Now, some of the others, such as a calcium carbonate, they become less soluble. And these are the ones, when you dump out an old water heater and those chunks fall out, those are the minerals that became less soluble and just turned into big rocks or big chunks inside there. The ones that you see coating out the element are these up here that became more soluble, and they turned into a film, and once they hit that hot element, then they attach to the element. So you've got some of each in there, and they all need to come out, because some of them are going to coat out and some of them are just going to fill up. So here's an example of a Gianobi type of heat exchanger, and I know it's a pretty small picture, but you can see inside some of these, you can see, about a third of these tubes are plugged up with scale buildup in there. So what happens is when the burner's inside this heat exchanger, the hotter these metal surfaces get, the more the minerals will precipitate out. And it's a big number. It's not a linear thing. I think the Rohr people told me it's a factor of 10 for every like 5 degrees in temperature that you increase, the minerals precipitate out much faster. So if you're running this boiler at 100 degrees for a low temperature radiant, you won't get so much scale, coming out of the solution. But you take that boiler up for a hot water indirect tank demand to 180 degrees, now you're going to see a lot more of the minerals precipitate now and stick into the inside of there. So the failure mode typically looks like this. So there's my flame, my burner that's inside there is this color right here. That's the wall of metal, so that's the thin metal surfaces here, and this is the water that would be inside there. So what happens when you get the minerals that become attached to the metal surfaces here, you get kind of a little blister here. So you get a little, just like when you pull out your electric water heater element, you see a blister right over where it exploded and burned out the element. So now I've got this flame temperature over here, maybe 1800 degree flame temperature against this metal, and this metal might be, 5,000 to 6,000 thick. Some of these metal heat exchangers are pretty thin. And now I've got that buildup right here from the water. So now that's where I'm going to get a pinhole, because I get this high intensity heat buildup here because I'm not getting this temperature into the water anymore because I've got this little insulation, and I might even have an air pocket under there. I've got a little bubble that now the water is no longer touching this metal, and it's called impinging. The flame impinges on the metal, and that's where you're going to get the failure point. That's what's going to, that's where they're going to burn through first. And you can see here, this is an example of the thickness of the scale buildup and how it changes the heat transfer. In this case, we're showing it as fuel usage, but also the transfer of the heat from the flame to the water. So now if you're up in this range here with not much buildup on there, now look what happens to your fuel cost. So you don't have that 90% plus efficient boiler anymore. You're back to where you started with your cast iron boiler at maybe 75, 80% efficient, because you just basically put an insulation layer across your heat exchanger. You might as well just get in there and, put a piece of, film across that and insulate the heat from the fire away from the water is basically what you're doing, just through the minerals, through the buildup inside there. So what we do when we soften water is we take everything that's in this bubble. These are all those positive and negatives that I just showed you in that previous slide, and we attach these charges to this resin. That's the little zeolite beads, these little beads that are inside there, and that'll attract half of these, but it's going to leave all these behind. So we're going to just basically substitute some of these colors in here for the brine that we put in there. So we're not getting water that's 100% pure, number one, and number two, we're going to sometimes actually have a higher conductivity water from the ion exchange process from the sodium that was in the brine tank that used to go in there to backwash the bad things off the resin bead. It left behind the ion exchange of the sodium, and sometimes if you test the TDS of the water going into a water softener, it could be lower than the water on the other side of it because you loaded it up with the brine that you used to backwash the beads to wash off the calcium and the lime and the buildup that was on there. So maybe it's a lesser of two evils in some cases. I know in Great Britain right now they're trying to say, well, if our water's that bad, maybe the softened water is better than nothing at all. So they're trying to come to grips with maybe, softening with some chemical added to it to bind up what's left in there is maybe another solution instead of, going with the ionized water. So, we're still learning about this, but most of the lessons that we learn, they've already learned over in Europe, because they've had this issue. There's actually a water quality standard in some of the countries over there now that when the inspector comes and does the combustion analysis to make sure the thing's running right, they'll take a sample of water and say, well, your water is out of the range that's acceptable by this manufacturer, by the whatever they call the code over there, and you'll get a tag on it just like you would if the thing wasn't, if the burner wasn't adjusted properly. So here's what we call galvanic corrosion. Now this is where you have two dissimilar metals, and here's an example of steel and copper, and what's going to happen is the steel is going to give up to the copper, so you're going to get this erosion going on, or corrosion I guess it's called, going on. But the only way this will happen is you've got to have an electrolyte between there. You've got to have water that's in there with conductivity, the ability to carry that current, because that's what you're doing, is building a little bit of a battery here. If you took the electrolyte out of there, the minerals out of that water, you wouldn't have this corrosion going on there. So when we look at putting different types of metal together in the system, we look at a chart like this, and it shows all the different metals that are common in the heating systems that we see. And the further apart that they are in this chart, the more potential there is for this electrolysis, for this corrosion to go on. So if you're going to put a zinc, like a galvanized nipple in a stainless steel boiler, you can see how far apart they are on this chart. Now, if we put copper together with steel and we use a bronze nipple in between, we've got two that are fairly close together on this galvanic chart. There's not going to be as much potential for corrosion, which is why some people say, well, just put a brass nipple between your copper and your steel, and then you'll, here's steel, and if you put the brass between the copper and that, you've got a little bit of more protection. But again, you could put copper in any one of these or steel in any one of these, as long as you didn't have conductive water in there. You're not going to have this happening in there because you've taken, the connection, basically the electrical connection out that causes those two to react to one another. So let's see, what are we doing for time? Yeah, we're looking okay. So this is Jeff Person. He's done some webinars and some training with the Radiant Panel Association over the years. He's got a company in Ohio called Geosource One. He's let's see if I can pronounce it right. He's a hydrogeologist, so he deals with earth and water and stuff like that. That's his degree. So he breaks it down to really understandable things. And here's an example. He said, take just regular tap water and put a roofing nail on one probe and put a copper penny on the other probe and put your voltmeter on there and drop those two into the water, and that's what you're going to get. You're going to get just under 1 volt of electricity is being generated by the electrolyte, which is the minerals in the water, conducted between this copper and this galvanized coated nail here. Now, he said, if I went and got a salt shaker and put a bunch of salt in there and mixed it up and shook it up and stuff like that, he said, you're going to see the voltage going up. And he said, that's what happens when you get salt in the water. It becomes more conductive, and you're going to have more voltage. You get a better battery than you do with just, the plain tap water. So if you've got tap water that has a lot of minerals in it, you have a lot of calcium or lime or whatever's in those bubbles there, you're going to get the same thing happening. You're going to get more conductivity between those two and more potential to have a battery or have electrolysis going on in the system. So,
Bob, is there a particular range that you want to keep this stuff within if you were to use this method for testing? I mean, obviously, the lower the better.
Yeah, I think you'd like to have that down to nothing if you could. If you had water that was filtered, I don't think you could get any current, any potential being generated between the two, because there's nothing between them that's connecting the two of them. So stripping everything out of the water. I've never asked Jeff that, is how high he's measured or how low he's able to get it from just using tap water like that. But we'll get on to, he's got some other examples where he's using deionized water to show you the difference here. So he's a pretty sharp guy to listen to. He's certainly knows his stuff and can explain it in understandable methods. So that what we really want to do is we want to demineralize, which means taking all the minerals. It's sometimes called deionized. It's either DI or DM, DI for deionized or demineralized. Ions, minerals, it's really the same thing. But what we want to do is take everything that was in those bubbles and take it out and get it down to this right here, demineralized water. We're going to end up with just H2O. That's what pure water is. Now, to do that, we would have to put some kind of media, some kind of resin in there that can take the positive and take the negatives out. And we can do that. It's pretty easy to blend these beads to do that. But what happens when you do that is you can no longer backwash this with an ion exchange, because there is nothing that you could run through there that could wash both the positive and negatives off. I could get rid of part of this by doing an ion exchange, but I don't want that left over, because then I'm going to end up with the salts in there. So I've got to come up with a resin that can do both, all the minerals that are in there. And so basically what we did is we went to a resin company and they said, well, tell us what you're trying to do first of all, and we'll see what we can come up with. And we said, well, we're trying to purify water that we put in the boiler or solar geo system, so we don't get corrosion, so we don't get mineral buildup, and so we don't get all these problems. And we explained, what we see as the problem. They said, well, yeah. He said, we can blend a resin to do that. And he said, we'll blend a resin that has some positive and some negatives. And he said, not only that, he said, we can bias the resin that we put in there. And I don't know if anybody else is doing this in the industry right now, but he said, what we know about most tap water out there, that it's going to have more of some of these than the others. He said, that's just the way water goes because of what it runs through. So he said, we'll make a bias where we'll give you 60% of one and 40% of the other. He said, that way your resin bed will last a lot longer than if we just sell you a 50-50, which is some of the other companies that are out there just using a 50-50, because it's a cheaper resin. Unfortunately, the good resin is the more expensive stuff. So when you put 60% of the good stuff and 40 of the other, it's a more expensive resin to buy. So this can solve our problem. The issue becomes now is that you can't backwash it. So once you plug it up, once you start filling it up with these dark brown beads in here, you'll get to a point where your meter on the top is going to say, well, I'm not, getting your water down to the TDS number that you want anymore. It's time to change the beads out. Now, they can, if you send those back to the factory where they make them, and there's a couple places in the U.S. that can do this, they can wash and reuse these resin beads. I hate to throw out anything that's still got a life in it, but he said, don't send us back, 50 pounds of these. He said, send a semi-load back, and we'll be glad to backwash them for you and send them back out or rebag them. So, if we get to the point where we see that many of the beads out there, if somebody would collect them at different locations and we can get them all back there, they just run them through a real caustic, like a lye solution, and they can, the beads don't wear out. They just plug up and have to be backwashed. So for right now, what we're saying is, if you're just doing small systems, once these beads plug up like this, just take them out and replace the beads, and you're starting over again. So the main number that you want to look at is you'll watch the TDS meter. It says creeping up, creeping up, creeping up. It's telling you that this is starting to happen, and you're getting down to where you filled up your beads with the minerals, and you gotta start over. So the simple thing, the best way to check water from this point forward is what the TDS of the water is. And it's a very simple meter. You can see, we sell them, you can buy them online. Pool supplies have them. We went with a meter that does two different readings. It's got the two probes in here that read the conductivity of the water is really what you're reading. It's just an ohm meter at the end of the day. And this one over here is a little porous glass bulb that reads the pH of the water. So if you're testing glycols and you want to see what your pH is, one meter will do both things. So now, the other thing, if you get water completely pure, it becomes really hungry water. It becomes aggressive water. It's almost like it's got a low pH. So we want to get the water down to a level where it's not going to scale out, but we don't want to make it too aggressive that they can eat through the copper pipe. Now, what we're finding and what we found is even if you put it in under 10 parts per million, if you got it down to 0 parts per million, what will happen within a couple of days of running through that system, it'll just pull some of the metals out of the system, maybe some of the copper, some of the iron, some of the steel, and it'll drive this number back up, and the pH will go back up too. So it's just binding up some of the products that are in there, not to the point where you're going to pinhole through the system, but just taking it up to about a 10 parts per million. I'll show you what some of the boiler manufacturers are telling you what the number is that they want, that they find is adequate. Now, the other thing that we learned is if we go much lower than this, that the low water cutoff probes don't work anymore because they need some conductivity in the water to read that resistance through the water. In fact, we had a contractor call us this week from up in Canada. He said, I put the water from the hydrofill in my systems and I can't get the boilers to fire up because the low water cutoffs are blinking in there. And we said, well, what did you put in? He said, well, I got it down to 5 parts per million. And I said, well, you got too good of water in there, really. So I said, what I would do is put some Fernox or some Rohr. I said, I'd rather put some chemical than putting some hard water in there, because then at least you're putting good stuff in instead of just, mixing some of the regular tap water to get your TDS up a little bit higher so that your low water probes will make again. So this is another slide from Jess Person. He said, well, you can read this yourself with just your ohm meter. Just go out to your truck and get your ohm meter and stick it in a glass of water, and you'll read the resistance of the water. So here's water. I think he fills this drill rig. He's got a big drill rig that they drilled their geo boreholes with, just from a fire hydrant somewhere in the city where he works. So he said, this is just regular, city tap water. So there's the resistance of the water right from the city where he's at there. And he said, here's water after he runs it through. He's got a big deionizer that he's had for years, by the way. He's been doing this for a long time. So you can see quite a difference in the resistance of that water just by stripping the stuff out of it. And this wasn't, crazy bad water to begin with. It's just that it wasn't this good of water. And the only way you got from this to this is running it through a deionizer column. So I will say that the ohm meters, it's kind of sensitive to how close the probes are together. I tried this myself, and I found, well, if I put one probe on this side of the charm, one over here, the readings really get pretty wide. So, and that's what you'll see if you go back a slide here. On these meters, these two little stainless steel probes are about 1/4 inch apart in there. And there's also a little microprocessor chip inside here. It's more than just an ohmmeter. It does a correction for the temperature of the water, and it's got a little bit more logic in it than just a meter that you would have out on your truck. But that's all it's reading is the conductivity. I don't know if you can see it here between the two probes that are in there. And if you want to just get a rough idea, you know, you can just stick your ohmmeter in it and see if it looks like this or if it looks like that, and that'll tell you that, you know, yeah, I got to do something with this water. So here's I got 4 or 5 different boiler manufacturers. This is right on the installation manuals on, I don't know, Lochinvar, Triangle Tube, Lars, and I think Viessmann is where I pulled these from. Now, it used to be, it was pretty simple like that, and they'd say, okay, just less than 7 grains of hardness and you're fine. Well, they're finding that they're putting a little bit more information in there, and this is probably the Viessmann one because it's in metric units where they're using centigrades and they're using the conductivity in a little different number in milligrams per liter instead of, you know, parts per million or grains per gallon. So, but what you're finding here in this picture, I don't know which brand this was, but they've got some pretty tight numbers. So you can see less than 50 parts per million of calcium, magnesium, total hardness here of 100 parts per million, chlorides, sulfates. Now, it would take a special meter to test for all these different things, and that would be a pretty expensive test kit to be able to go to a job and actually test for every one of these. But everything in this bubble, in this picture here, would come out as a TDS number. Now, I don't know if I've got a lot of this and a little bit of that and a lot of that and none of this. When I read the TDS, I just know that if my TDS number, like down on this one here, they say TDS less than 150 parts per million or 8.77 grains. So they're not breaking it out into what it is. They're just saying, just get it below this, and we'll know if you put it through a filter that got it below this number, that you've addressed pretty much everything that's in this bubble. Now, some of these are important, more important than others if you're doing stainless steel boilers, because some of these, like chlorides, are pretty aggressive to like stainless steel and aluminum boilers. So you'll find if you put in the stainless steel indirect tank, they're probably going to have a number or a label right on the side of the tank, and no Crown, and some of them have been doing it for years, that they're just talking about chlorides and say, keep the chlorides under a certain level. I think Crown's got like under 100 parts per million chlorides on their stainless steel indirect tanks. They're not as concerned about some of this. This one is the one that's going to corrode through their tanks. They're most worried about that as far as warranty issues. Certainly, if you got this stuff in there, you're going to start scaling out and, you know, filling the tank up with lime. But this is the one that's going to give them more headaches. So I think what you're going to find, the manufacturers are going to keep beefing this up in all the installation manuals. So going from this to this, I mean, some of them actually have a full page now. They tell you, okay, if you got this going on, you need to do this or you need to do that. Because if you're outside of any of these numbers and that boiler goes back for a failure from a failed heat exchanger, and they either send some of the water back or they, you know, check it right at the wholesaler. And if you're out of range on any of these numbers here, you really don't have a boiler warranty. And it's, you know, that's going to be a tough conversation to have with a homeowner if you say, hey, your boiler's got a pinhole. And by the way, you know, that 20-year warranty they told you you had, well, you don't have a warranty. In fact, if I put a boiler in and I didn't assure that I met whatever goes with the boiler you're going to put in, if I haven't met these criteria here, I don't have warranty on that boiler from the day I walk off that, the very first day I put that boiler in and walk away from it. If I haven't addressed all these things, I really don't have a warranty on that boiler. And like I said, the boiler manufacturers are going to start clamping down on that because it's costing them money to just keep giving us heat exchangers for warranties when it wasn't their fault. Now, some of it was their fault, and they admitted that, but here's the deal with chlorides. Now, chloride in itself isn't a bad thing. It's a naturally occurring element in the earth. It's, you know, it makes water taste good. But here's where it starts to get a little lopsided. So at this level right here is about when you can start tasting it in water. You'll get kind of a salty taste because it does taste like table salt or something in your water. So it'll start going after all the, if you start seeing that green fuzz on your aerators, on your faucets, or, you know, around the packings on stems on ball valves or stuff like that, you probably got high chloride levels, because that's what it's going to do, is it's going to start, you know, breaking down those metals. And that's typically how it shows up on a domestic water system, is that kind of bluish green fuzz that you see on things. And here's an example of what it does to a water softener. So they say it'll shorten the life 1 year for every 100 milligrams per liter over the first 100 milligrams per liter. Now, you could, again, turn that into parts per million if you wanted to read that on your TDS meter. And by the way, this is my source for all this information that I got above here. So But in addition to the chlorides, it's the temperature. So once we put water that has a lot of chlorides in a boiler, or we put it in an indirect tank and we start heating it up, that's when it becomes even more corrosive, especially if we've gotten domestic water where we're starting to get oxygen from the water that's coming in there, replenishing those oxygen levels. So this is usually where it goes after the stainless steel. Whenever you weld a metal together, you kind of break down some of the metallurgy. So when they weld stainless steel together, even with a good TIG weld process or the right type of wire feed welder, they still have an issue with what's called the crevice corrosion, either where the metal laps over itself and they weld it, or if it's a butt weld and you just have you can see part of the seam of the weld in there, that's where the corrosion typically happens. So when you see an indirect tank or a boiler fail, oftentimes it's where they've welded the heads onto the tank, or they've welded a well into it, or they've welded a nipple into the tank. That's usually where we're going to see the pinholes develop first, because the metal's most sensitive there. So as I talk to the people in the industry, I work with the guy here in Springfield, Missouri at Rohr Waters in my hometown here. And I talked to the chemist there, and he said, the chloride levels have been just creeping up over the years. He said, I used to test water that would come in here and it'd have maybe 100, 150 parts per million, still acceptable for most of the manufacturers. But he said, in the past 3 or 5 years, he said, I'm getting water that's coming in at 300, 350 parts per million chlorides. And it's being sent in as water that comes right out of a faucet, tap water, city water that's just being sent to them. And he's seeing those high chloride levels. And so he's been paying attention to this. And he said, you can send me water from anywhere in the country. And he said, I'll sample that water without even looking at the return address on that container that it came in. He said, I can tell you where that water is coming from just by what the levels are of the different minerals that are in there. And he said, if I see these elevated chloride levels, said, most of the time it's going to be coming from a place where they're using a lot of de-icers on the road. So it's going to come from Minnesota or Wisconsin or Colorado, certainly not from Mississippi or Texas, where they don't do a lot of road de-ice. And he said, here's the issue. He said, over the years, they've been putting chlorides on the roads as de-icers instead of just using regular rock salt, which is what they put on when I was growing up. You see that on the road. It's those little white beads that you see on the road. He said they've been using more and more chlorides, and he said there's good reasons for them to want to do that. Is number one, it works down to a much lower temperature than rock salt. Rock salt, about 5-degree ambient temperature outside. The rock salt isn't very effective anymore. So the other thing, when they put rock salt on the road, is they spread it with those spreaders that you see where they just throw it on the road as they go up. He said, some of it bounces off to the side of the road, some of it doesn't dissolve. If the pavement isn't wet, he said, then the plows come and they just plow off the salt that they just dump down with the truck right in front of it. So he said, it's not really a great way to do it. So when they go to chlorides, what they do with the chlorides is they put it down as a liquid. So they'll mix the chlorides into water, and you'll see those tank trucks with the little spreader bars going up the highway now. And what they'll do with the chlorides is they'll put it on before a storm is going to hit. So if a storm's coming into Colorado tonight, they're going to get out there tonight with these calcium spreaders, and they're going to put this liquid on the road. And for them, it does a couple things. Is number one, it stays on the road better because it actually gets into the asphalt, it gets into the concrete, and it stays there. And the other thing, once they've got that wet layer on there, he said now they can follow up with rock salt, which is cheaper, and they've got a lot of that. And he said it will dissolve the salt right away because now you've got a wet road that isn't freezing, and it's going to melt the rock salt. So the rock salt becomes more effective if they put it on behind the liquid calcium chloride. So they're using these in combination with one another. So where do you think all this ends up at the end of the day? And I got this from the MoDOT Michigan Department of Transportation. I went to the one in Minnesota. I went to the one in New York recently, and I also went to the DOT websites for Colorado and got this information. So what they've been finding, they've been studying this up in Minnesota because they put a lot of this on the roads up there, that 70% of that stuff, that this calcium chloride that they're putting on the roads, is being retained by the watershed. So he said, if you go around the lakes up there where the highways are close to the lakes, he said, along the shore, you're seeing the vegetation is starting to go brown. The fish are dying there because it consumes the oxygen when it breaks down. So if the fish aren't dying from the calcium in there, they're dying from the lack of oxygen. And you see the algae blooms along the lakes that they've never seen before. It's all related to these chlorides that are going into the aquifers. So this is an example how powerful that stuff is. So 1 teaspoon in 5 gallons of water can start to affect the fish life and also the plant life. The other thing that's doing, when you drive up the highway Interstate 70 there in Colorado in the wintertime, you'll notice a lot of wildlife along the side of the road because they're coming down to lick up these chlorides. So, you know, whether they got the sheep or the goats that are coming off the side of the mountain there, Mark, and you see the bison or the buffalo, you see the deer, you see the elk, they're coming down because there's so much of this stuff on the side of the road now. They like to lick that up. And in Colorado, that Interstate 70 going up out of Denver, they put between 200 and 400 pounds, sometimes as much as 500 pounds per lane mile on that road. So think about however many miles it is across I-70 from Denver to across the top of the mountains and down the other side, and multiply that times how much they're putting on there. It's quite a bit of chemical that's getting in the aquifer there. So Paul Smith's College, I was up in New York last week in Western New York, and Paul Smith's College in upstate New York has been doing a study since 2010 on the chloride levels in the lakes up in the Adirondacks and seeing how much it's going up and how it's affecting the vegetation, the fish. And the other place that it really is starting to show is in, and then put a picture of that in there, is in the vehicles. Because what happens with chlorides is they stay wetter longer, which is one of the good reasons that they put it on the roads, because once it's on there wet, it's going to stay wet. It's not going to get plowed off. But if you go and you reach up inside the rocker panels of the fender on your truck or your car in the wintertime, a week after you're down in the city and it's dried out and the sun's been out and it's dry outside, you'll reach up in there and you'll still feel this moist sediment up in there. That's the chlorides, because they just hold their water for a long period of time. So it's like a multi-billion-dollar problem for vehicles that they rot through, because the chlorides are so much more aggressive than the salts to begin with, and that they stay up in there and they stay wetter longer. So it's hard to get rid of them once you've got them inside your vehicle, inside the seams and stuff on the fenders. The other thing I noticed when I come back from Wisconsin in the wintertime, I bring my truck in my shop and I wash it off. And I go the next morning after the radiant slab dries that, and there's this like black film on my slab. And I take my pressure washer, I take my hose, and I try and get rid of that. I take a broom and I scrub it, and it just doesn't go away. You come back 2 days later, and I broom it again and put water on it, and I still have some of this black film, and that's the chlorides. They're actually getting into the pores of my concrete that you can't even, with the pressure washer, they don't even want to go away. So good news for the people that are de-icing. Bad news for us if we're putting this into our systems or into our vehicles or into our aquifers. It's just not, I don't know what the answer is. People aren't going to drive on icy roads anymore. There was a time when I grew up where all they did was the intersections in Buffalo, New York. They put a little rock salt, or sometimes it was sand or even road-based gravel on the intersections, and you just learned how to drive on, slippery roads. But that's not, I doubt that we're ever going back to those days, and certainly not in my lifetime. So this is going to be a problem that we're going to have to figure out what to do with. Now, for you and I, for our boiler water, that's not that hard. All we have to do is either buy water, which you can buy deionized water, and this is right off a website that they'll send you 55 gallons of deionized water for about $6-7 a gallon or more. If you buy small quantities, it gets a lot more expensive. So you can buy it. You can go to a place where they can do this for you. Here in town, I used to go to Culligan, and he said, well, just bring a 55-gallon plastic barrel. And he said, I'll just sell you water. He said, back into my shop. And he said, I'll just take a 1-inch hose and fill up that bucket for you. So you can buy it. You might find somebody locally that can do it for you, or you can make your own water. And so that's what we do at Caleffi. We said, well, let's just make a portable device that you just hook a hose on the bottom of this. It's got those resin beads, that 60-40 blend of resin beads in here. And then there's a little TDS meter right up here. So as the water goes in here, you look at the meter and see what it's reading. You get it down to under 50 parts per million, which is what those manufacturers were looking for there. And so you just adjust this ball valve down here to slow it down until you get to the level you want. Now, what will happen is you'll see after you put maybe 1,000 gallons through this, you'll see that meter starts creeping up, and you've got this thing, you're balling it down, and it's still creeping up. Well, that's an indication that you plugged up your resin, and it's time to take it out and replace it. So these have been around for a long time. These aren't unique devices. There's other people that use this type of water if they're washing windows, for example, or if they're blending chemicals, blending glycols, or if they're doing, pharmaceutical work, they're going to run their water through it's called a tower, is what they call this device right here, deionizer, demineralizer tower. So once we got to the point that we knew what we wanted in it, and we found a device that we don't make this, we partnered with somebody that makes this cart, and this, it's a nice stainless steel cart, by the way. we said, well, how are they going to change the beads out? We can't have them just dumping out because they're like little ball bearings. You get them on the floor and you'll break your neck trying to walk on your floor because they get everywhere. They're like, 1/8-inch diameter ball bearings everywhere. So we said, we got to make it a little bit more user friendly. So we came up with the idea, well, let's just put the resin in a bag. It looks like your grandmother's old stockings is what this looks like. And then once they're used up, you pull the bags out and you drop new bags in. Now, you can throw these out. They can go in a landfill. They're not toxic. They're not bad. But, I hate to put stuff in there that's plastic, knowing that it probably won't break down for a long time. But there's nothing, in there that the EPA or anybody would come after you and say, you're dumping this in there. But that's the key. So we have a 2-bag one and a 4-bag one. So then the question becomes, well, how much can I do? How much water can I filter before I have to change the bags? Well, it's just going to depend on what's in your water. If you left a lot of crap in your water, like solder flux, or, there was dirt and stuff in your water, or whatever it might be, it's going to filter less than if you put good quality water. So the very first thing that I would encourage everybody to do on every system is just flush the system out. Just get this type of stuff. Well, hopefully you have a rat in there, but get the solder flux out of there, get the oil out of there, get the dirt, get the shavings, get the cutting oil, the assembly lubes, the drawing fluids that are inside your copper pipe. Get all that stuff out of there. Now, to do that properly, you really need a detergent in there. It's hard just to get all this oily type of stuff out with just, water, even hot water, from heating the boiler up. So all the hydronic companies, Rohr, Fernox, Sentinel, Hercules, Rector Seal, they all have some sort of cleaner that you could put in your system, and most of them are just a really strong soap. It's just like a detergent, like you would put in your dishwasher or in your wash machine, and it'll break down all these, oils and fluxes and piped open stuff like that, and then flush it out, and then go in and put in good quality water. Now, if your fill water on your job is good, there's no reason to go through all these steps with the demineralizer. But if you're above that number of, 150 parts per million or something like that, you really should look at putting it through some type of filter. Now, you could run it through an RO. The problem with the reverse osmosis, it takes quite a bit of water to make it. Used to be about 3 to 1. They've gotten a little bit more efficient. We're used to take 3 gallons of water would go down the drain for every 1 gallon that you got out of the RO. So, if you're paying for that water, that gets expensive, and it's slow. It takes quite a few hours to get even 5 gallons of water. If you go to a house that's got an RO and you hear water running down the drain by the kitchen sink all the time, is a dishwasher? I got a leak going on? Well, no, that's the RO wasting water to make the good water. Another thing you could do is you could distill the water. And true distilled water, you'd have to boil it and collect the condensate on a stainless steel plate and let it drip into a bucket. Now, you can imagine what it costs to take water from 55 degree out of your well up to 212 degrees and collect the condensate. So that's an expensive way to purify water, although it does make about the same water that you would get with reverse osmosis or a demineralizer. It's just not a very cost-effective or fast way to do it. So after we looked at those, really the simplest way and the best way, what we wanted to do here is make it so that you could take this on a job and get your water for about 35, 40, 50 cents per gallon to do it on the job site. Now, that's going to depend on how bad your water is, because that's how fast the resin bed's going to plug up. So that we found is going to be cheaper than going and buying water by far. It's not going to be anywhere near this, and probably cheaper than driving somewhere with a barrel on your truck and backing in a Culligan and having them filled up, because now you got your travel time and home water. So we've got a bunch of these out there, and we're finding that people are getting clever ways of doing this. So we've got one of our suppliers up in Michigan, I think it is. What he's doing is he owns a couple of our units, our hydrofill units, and he'll just fill up barrels. So you can come in and say, I need 55 gallons. So he'll fill up a 55-gallon barrel for you, or he'll fill up a 250-gallon, what they call a tote. It kind of looks like a pallet with a cage around it and a plastic tank inside the cage. Those things hold about 250 gallons, but keep in mind that times 8.33 pounds per gallon, you got, 1,800 pounds. So you're going to need a vehicle that you could put that kind of weight on if you're going to get 250 gallons of water and start driving around with it. So
that excludes Nissan pickup trucks, huh?
Yeah, maybe a 3/4 ton pickup or a flatbed truck would handle that, but I don't know. You'd probably want a trailer or some way of doing it. Now, I guess if you're a good customer, he would probably deliver that to the job site with one of their, a truck that they can unload it off the tailgate or something like that. But So here's what I would like to see happen with every system. I'd like to see it flush it out with a detergent, get one of these kits right here. I like these kits because they come with a cleaner. They come with a hose bib connection right on here. You just screw it on a boiler drain or a fill valve anywhere, put it in there, run it for a day or two, come back, flush that out, and then do the same thing. Most of them now come with the 2 aerosol cans, one for the cleaner, one for the inhibitor, and just put your good water in, then put your inhibitor. Because what you're going to get with an inhibitor is, number one, you're going to get that pH back up where you want it. You're going to buffer the pH. You're going to consume any oxygens that might have been left over in there. And what the other thing that these chemicals do is they put a little film provider in there. So if you cut open a piece of copper tube that this had run through for a couple weeks, it almost like somebody got inside that copper with a magic marker and just put a very thin layer inside that copper tube. And that's going to protect that copper tube from getting attacked by aggressive glycol or aggressive water if the pH ever did drop down. So it's kind of like you're rusting or anodizing your tube to protect it from getting any further corrosion. In fact, when you buy anodized aluminum, that's what they've done to it, is they've rusted that aluminum so it doesn't corrode away like if you're using it outside. You want to use anodized aluminum because they've done that for you. They put a film layer on it by just anodizing that at the factory. So that's really what this chemical is best at doing, is putting that little film provider so you don't have to worry about, getting especially when we've got multiple metals. We've got stainless steel, we've got iron, we've got copper, we might have aluminum in there, we've got all different alloys in there, we've got a lot of different types of products, and every one is sensitive to a different thing in your water. So if you just put a film over everything in there when it's new, now you've got a protective layer that it doesn't matter if you've got the dissimilar metals or you've got soft aluminum that might be sensitive to a low pH. You've kind of insulated that potential away from it by just putting a fine internal coating in there, so to speak.
Is that what they refer to as a passivation chemical?
Yeah, that could be that's exactly what they call it, and that's what they do when they anodize aluminum. I guess they use an acid or something like that they etch that on there, and that's what they're doing. Is just it's called pickling sometimes. There's different words for it, but I think people just come up with different names for it. But that's what they're doing, is they're just trying to treat the surface of that metal to protect it. Mark, you've probably seen them up in Colorado. Some of those buildings with the metal roofs are rusty.
Yeah.
Well, they rust that metal, and then they put a clear layer over it, and that protects the metal underneath it. It's called a Corten process, where they just rust it before you get it. So you don't.
I've actually got some of that on my fireplace.
Yeah, so you don't have to wait 20 years for it to do it on itself, and that's in there to protect it. So
the days of using TSP to wash out systems is pretty much in the rearview mirror, is it not?
Well, they've taken the P out of TSP. The EPA did that. It's probably been 10 years or more now. You used to be able to get at the painting supply places really strong TSP, but even the stuff, if you go to Sherwin-Williams or people that sell you TSP for cleaning walls before you paint them, they'll tell you it's nowhere near as powerful as it used to be. So, the phosphates are bad for the environment, but they certainly were good cleaners. But I think really the best thing is use one of the hydronic chemicals, because they can put soaps in there that aren't, as regulated as what you buy, at the Home Depot, for example. When you buy TSP on the paint shelf, it just isn't the cleaner that it used to be. So the other thing, if you use a hydronic cleaner, it's got good stuff in it. It's got some of these other chemicals in there that are going to do good things for your system instead of just, washing the dirt and debris out. It'll have some oxygen scavengers, some buffers and stuff in there. I think the Rohr people told me there's about 27 different ingredients inside their cleaners and their inhibitor chemicals. He said it's not just, one simple thing that we put in there and sell it to you. He said there's quite a few different things. He said we got to do that because it's got to be able to work with all these different mixed metals. He said what works for aluminum you couldn't put in the stainless unless you put another ingredient that buffers it down. So he said it gets really complicated. He said it took him years to come up with the formula to be able to work with the aluminums and the alloys and the stainless and all the different things that are out there. So I'm not going to turn into a sales spiel, but this is basically what we've got with our hydrofill. That's about the flow rate that you could run through it, depending again on how crappy the water that's coming in here is how fast you can purge it through there. The other thing I learned a couple years ago, I don't know if I put a picture in here. Now, here's another thing that you could do and say, well, this job holds like 1,000 gallons of water. I don't want to drain all that water out. It's going to take me days to go around and purge all the radiators or whatever's in there. You could just put in like a, Webstone valve or something like this that you could ball down the center and just bypass through the hydrofill here and just let it run for a week and come back and test it again. and just keep running it through there until you get enough of it bypassed through there. Obviously, you're going to have to regulate this so you get enough flow down to your boiler, to your system, that you don't starve it for flow. So you just have to adjust this, let, maybe a gallon or two per minute go through here, and the rest of it go through your system. And just over the course of time, you can just, keep going back and just keep checking it until you pull it down to that level that you want to be at, so you don't have to start from scratch to be able to do this. Now, one thing I will caution you about, the beads in there, you can't put 180-degree water through those beads, or you're going to end up with a melted bead. So I think up to 140 you can run these things without damaging the beads, or the plastic body of the card here too is rated at 140. There was one other thing. We do make this too. Now, let's say you fill up a system and you leave. You say, well, what if somebody goes to service a pump or change a zone valve someday? How are they going to fill it? So we've got this little setup here that you can just take it with you. If you got enough money in the job, just leave it on the job site. So any water that goes in, if air burps out of it for a couple days, you're going to go through this little cartridge here and make sure that you keep putting, this is just a little, throwaway cartridge. That's the same beads that are inside the other one. It'll just do, about 30 gallons of water. So it's enough just to take any refill water and filter it for you. So what do we got for time here? Give me another 5 minutes and we'll get through the last thing. So I'm getting different. These are some of the guys from Heating Help that said, well, I'll start sending you pictures every time I change out a boiler, what we find in there. And these two here concern me. And what these here, this is called magnetite. If it's black water and you put a magnet in there and it sticks to a magnet, it's called magnetite. This is the next step called hematite. If it goes red like that, it means it's gotten more oxygen than this did, and it's gone to the next level, which is rust, basically, which is what they make paint out of, by the way. Red paint is made out of this iron oxide. That's how they get the red in it. So what's the issue with that? So here's the difference between magnetite and hematite. There's a different formula. You can see the O, more oxygen here. But what that does is it turns into a very fine particle. In fact, this is magnetite. So I talked about 5 micron being the thickness of a human hair. Here's what it looks like under a microscope. So when you have this in a system, you drain it out, you think, oh, it's just kind of inky, dirty water. Well, no, it's got this stuff, and it's got magnetite. If it sticks to a magnet, it's got, it's metal particles from somewhere in your system that have been broken down because oxygen's been getting in your system. So where you're going to see this most often is any of the old radiant tube systems like the polybutylene, some of the solar roll that are out there, some of the early rubber tube that didn't have any oxygen barrier at all. Every day that system is running, oxygen's getting through there, and it's forming this black sludge. And you can get enough of that sludge in there that it'll actually plug up the tubes where you just have to abandon those tubes because it's heavy. It's got metal in it. So if you get enough of it in there, you can't even flush it out with high pressure air. It just goes right in there and just sludges out. So,
Harvey had a question for you. Wants to know what you can tell us about anodic protection in a hydronic system.
Yeah, so anode rods. So anode rods are sacrificial rods that you would put inside. Typically, you see them in a water heater. And what they're in there for is they sacrifice themselves. They give up themselves. They break down so that it doesn't attack the metal inside there. Now, typically, you're going to find that in like water heaters that are made out of steel. You typically see them in stainless steel. It shouldn't be a problem in a boiler because you don't have the oxygen getting there. See, in a water heater, since every time you open the faucet, you're getting new water, new oxygenated water in there, that you have that potential for that corrosion. And that's why the sacrificial rods get consumed in there, because they're seeing fresh water all the time. Now, if your boiler system is in fact sealed and closed and oxygen isn't getting in through an air vent or through the wall of a radiant tubing that doesn't have a barrier on it, there really should be no reason for an anode rod in there. It's not going to get consumed because there's no oxygen to allow it to break down and get consumed. So again, you'll see them in a steel type, even enameled or glass coated steel tanks. Like Badera's had electronic version on some of their tanks for a while, but the tanks that we sell, we actually send them out with 2 anode rods just to try and extend the protection level of it. But it's going to be a magnesium or aluminum. It's going to be a metal that can break down pretty easily, a soft metal.
I have seen them on Ajax boilers too.
Yeah, you might see them on some boilers, but again, that's a steam boiler, something that's getting water added to it occasionally, right?
No, these were actually hot water boilers, but with that particular model of boiler, you can use it for either or the other. Just
a steel boiler.
put the right controls on it.
Yeah. Well, there's certainly no harm in putting it in there. It's just that know that if you put an anode rod in a boiler and it breaks down, you're going to get whatever sludge that forms when it breaks down into your system. So you'd want to make sure that if your anode rods are disappearing in your boiler, you're going to have to flush out whatever the aluminum or the magnesium sludge that they leave behind when they break down is in your system somewhere. Now, here's an example of a Heatmeister boiler that he took out. Now, this is it's on its side. You can see a cast iron boiler, and it's got magnetite in it. Now, in this cast iron boiler, since there's very low flow velocity going through a cast iron boiler because of the big open passageways, it just started building up in the bottom sections here, and it just, until he cracked open that boiler, nobody even knew there was this much in there. Now, think about what that's going to do to the efficiency of that boiler when you're trying to get fire, let's say, from the burner into the water that's inside here, and you got that much of a sludge, that layer of a buildup. In fact, I think this, Mark, is one of the jobs that he wasn't even able to salvage some of the tubes. They had plugged up with so much of this sludge in there that he couldn't even blow it out and salvage some of the zones.
Probably one of the non-barrier systems that he gets to work on up there.
Yeah, so now here's another thing that's starting to happen in our industry, and this is, I heard this last week back in New York that in 2018, the DOE is going to say every pump, even the small pumps, have to be ECM motors. Right now, the Department of Energy said anything 1 horsepower or bigger has to have an ECM motor on it, and they're going to say every fractional horsepower. I heard 2018. Now, they usually give us a grace period just to get rid of the inventory that's out on the shelves as far as the old style pumps. But so this is a permanent magnet motor. This is an ECM motor. So this is it'll lift about a 5-pound weight. So there's a hole through this shaft, so you got an impeller out here that's in the volute of your pump. So whatever fluid is going through this system is what comes out and lubricates this it's actually a bushing, it's not a bearing, it's a ceramic bushing. So if you've got any crap in your water, you've got the potential for that to come through there and get in between this rotor and the rotor cam. Now, when we started showing these, we got calls from the pump people, and they said, no, don't be telling people that can happen, because what they claim, and I believe this, and I would agree with this, they said the water that goes inside this the very first day you turn this pump on stays in there. The water doesn't come and go. It just is trapped in here. Now, if you overheat this and turn it to steam and it leaves, obviously new water comes in. So they said this stuff can't come in through that shaft because the water's not going back and forth. I said, well, if I've got a 5-pound magnet here and I've got magnetite out here and I've got a hole in there, you're telling me that magnet's not going to pull the stuff through the water that's in there, whether the water's coming and going or not, and getting in there. I said, because this picture right here is an actual picture. This isn't something that we fabricated just to show, how the magnetic particles stick to the ECM type of pumps. I said, we've got a dozen of these pictures from all over the country that look just like this. So you can tell people whatever you want, but what I'm telling you is this, in fact, is happening. So, now they're saying, well, we're putting a bio barrier in here. We're doing something inside the shaft so this can happen. I said, well, if you put a cotton wick or you put a filter or anything in there, I said, eventually that's just going to plug up with this, and now you're not going to have any fluid out here. So I said, you can't move the problem downstream without, having something that you're going to have to service inside there. So it's true, and these are just some of the examples out there, and you're going to see more and more of these. And I would say by 2018 or 2020, this is the only type of pump that you're going to see on the shelves out there. So you got to come up with an idea to make sure that you're going to protect that. So there's the rotor, and it goes inside what's called a rotor can. So the next time you take a pump apart, you take it, the bolts out here and pull it out. Take your pocket knife or a couple screwdrivers, and you can wiggle between these two surfaces, and you can wiggle this off of that. Now, it comes off kind of hard because there's actually a bushing in here that goes into, but you can actually split these apart so you can see what's going on in here. So this rotor spins inside this can with only a couple thousandths of an inch clearance between that and this. So this spins, this is permanent. And so what happens is that that magnetite gets stuck to the magnet here, and eventually it starts, first of all, it'll start slowing it down, and eventually if you get enough of it, it won't start at some point. You got, your pump is bound up because of and there's an example of what the magnet looks like. So it's not, again, the fault of the pump, and I think the pump people are going to start saying the same thing that the boiler people are saying. If you're sending those pumps back that have bad water in them, whether it's got magnetite or whatever it might be in here that's getting inside there, it's not the pump's fault, and we're not going to warranty that pump because it's just not. And, I see both sides of it. I've been the contractor that doesn't want to tell the homeowner, well, I got to sell you a new pump. It's not under warranty, or worse, I got to sell you a new boiler. It's not under warranty because, it was it was damaged by the fluid that's in there. And so that's the kind of magnet we're talking about. So there's the rotor can, and if you take and wiggle your knife between these two surfaces right here, you can pull the rotor out of the rotor can, and that's where you're going to see any metal particles in there that are sludged up. And that's that same one I showed you earlier. Once you wipe it off with a paper towel, that's what it should look like all the time in there. Anything that you add to that is going to cause a problem for that pump being able to spin properly. Oh, there it is. So that's before and after that same pump. And by the way, this is up in our building up in Milwaukee, and this is the third pump that failed on our building, and the first two failed, and we just sent them back to the manufacturer. Said, yeah, we'll warn you, it was a software glitch. You know, there's nothing wrong with the pump. We just had to, you know, fix a glitch in our software. And when the third one failed, I said, something's going on here. I said, there can't be three, and because this is over the course of 12 years now that this has happened. So this, I actually took this apart. That's probably my hands in the picture there. And that's what it looked like when I took that pump apart the third time. This is, I had a better picture of it back here. I'm sorry about that. Anyways, I took a white paper towel and I wiped it off, and I just had a palm full that, now my concern is why I have this in my system. Number one, we've got 32,000 feet of Kitech tubing in our slab that's hooked up with copper on a stainless steel boiler. So something somewhere in my system is allowing oxygen. The only way this can break down, that my expansion tank or my pump bodies or whatever metal in my system is breaking down, that's turning into this black sludge. And the only way that can be happening is oxygen's getting in there, which makes me wonder if something's going on with that Kitech tubing that we don't know about.
It's a parallel path.
Well, they disappeared from the market almost overnight, so somebody knows something about that. Well, the good news is it's a pretty easy thing to fix or to solve on your system. All you have to do is put a magnet up inside or a magnet around the outside. We make these. Boiler Mag up in Canada's got a couple of them they're coming out with now. You'll see more and more of the people that have, you know, dirt separators or even Y strainers putting some kind of magnetic device that we catch the crap here instead of into our pumps, because that's going to be a problem. And, you know, I said the pump people when we first started talking about this, and we knew this because this has been going on over in Europe, because, you know, the ECM pumps have been over in Europe since, 1994 or something? We saw them at the issue over there, Mark. So they've already been down this road. They said, we know what's going to happen with those pumps over there because we've been down this road. We've had ECM pumps mandated by the government over there. You know, the Euro pump standard over there has mandated ECM pumps for, 3 or 5 years now. So they said, we know what you're going to go through over there, and some of these products that we have had already been developed over there because that's how they're protecting the pumps over there. So it went from the pump manufacturers denying that this was a problem, and now they're coming to us and said, well, can you come up with something that we could put right into our pump bodies that we could do this right at the pump instead of having to add a separate device? So we're looking at some options for them that they could maybe somehow right in their casting or their forging put a place that a magnet could go in there. But you really need a chamber to collect that stuff. So once you pull this off, you don't want it, right in your pump. You want it to settle out here where you can keep it out of harm's way. So I think, I've got some other slides on glycol, but I think I've kind of run over a little bit already, but I could talk till the cows come home. But I think that's pretty much it. The other thing that I've learned is, this is from Dow Chemical. We had a Dow guy on last year that did a really good webinar for us, and he said, if you're going to blend any Dow glycols on the job site with water, this is what the water has to be that you put in there. He said, if it's out of spec here, he said, you're going to ruin that glycol the very first day you put it in there, because the inhibitors that they put in the glycol are in there to fix this in your water. They're not to fix the glycol. The glycol's fine. It's a petroleum product. The glycol's not going to go bad. It's the water that's in there that's going to go bad, and it's going to go bad from the stuff that was in the water when you blended it with their glycol. If you bought strike glycol and blended it with water that had higher parts per million of any of these, you've kind of used up that inhibitor package that they put in there, and you really should go back and buffer up that glycol by adding more of the inhibitor that they put in it. So that's why they're so adamant that either buy premixed glycol that they use deionized water to blend it, or if you're going to blend your own glycol, make sure that your water is, falls in this range here, or actually you don't have a warning on the glycol either, but nobody's really been, pushing them on that. So
you're making me think. I have glycol in my house up in the mountains, and I haul Denver water up there, which to my knowledge, is pretty decent water, but I think it's time to go in and do some testing and
Well,
see where we're at.
Well, that's it. I mean, if you're not testing, you're guessing. People think they have good water. And by the way, if you pick up a bottle of water, and it depends on what brand you get, if you read that, they say it's filtered water. And I'll bet a lot of that bottled water that we buy from Nestle or Coke or something like that is probably just city water that they ran through an RO, maybe a carbon filter to polish it up a little bit. Basically, they're stripping the bad crap that the city puts in the water, like the chlorides and the chloramines and peroxide, whatever they're using. They're using all sorts of chemicals out there because the bacteria are getting away from them, and they have to find stronger and different chemicals to treat something like Flint water. It's a classic example of how the chemicals they were using actually went the wrong way. They didn't fix the water, they made it worse. So as they put more of that stuff in there, when they filter water, if you read the side of a bottled water, it'll say filtered water, and then they add all this stuff back into it because it makes it taste good. Nobody would drink water if it was just deionized water. It would taste like medicine. It's a really flat, crappy tasting water. So in order to get you to buy that and drink it, they got to put a mineral package, they call it, back in. So they're going to put calcium and lime and magnesium. They're going to put stuff back in there. And oh, by the way, they put sugar in there so you get addicted to it. Some of them will actually tell you how many grams of sugar or sweetener, depending on what type of water you buy, that they put in there. So they made really good water from bad water, and then they turned it into kind of, bad water. Not bad, but, certainly not water you'd want to put in your boiler because they put the, the mineral package back in it. So the one last thing, and I don't think I put a slide in here because I knew I didn't have enough time to do this, but I went to an IGSPA show a couple years ago in Tulsa, Oklahoma, and I met a company called Purge Right, and it's a company out of Texas, and what they do is they go around and they purge out problematic, mostly big loop fields, loop fields that might have 2-inch diameter loops and stuff like that. And I said, well, why would I hire you to do that? I said, why wouldn't I just do that when I fill it? He said, well, the problem is you got to have a lot of flow to be able to purge a 2-inch pipe. He said, you're going to need to get that fluid velocity up to about 5 feet per second. He said, right at 5 feet per second, he said, that's when stuff will start coming out of your pipe, because he said it takes about 5 feet per second of velocity start moving particles through there. He said, you'll get air out, you'll get some fine dirt out, but he said, if you've got big chunks of whatever, stones or rocks or cell phones or whatever might be in the pipe, he said, you really got to get a really high flow velocity, 5 feet per second or higher velocity, to be able to move that stuff out of there, like that cast iron boiler I showed you a couple pictures back. Purging that thing with the auto fill valve or whatever is in there, you're never going to get that stuff out of that boiler until you get, a good enough flow that can move those solid particles. Now, in that boiler, it probably, wasn't an issue inside there for all the years it had been in there. But, if you put a new boiler in there, I thought it was right there. Sorry about that.
You went past it.
I passed it?
Yeah.
If you put a new boiler in there that's got a heat exchanger that only holds a gallon of water, and it's got small passageways about the size of a 3/8 copper tube, you certainly don't want that sludge that was in the bottom of that boiler back into your system. So you got to get enough velocity to do that, and you can just look that up on any pipe sizing chart. It'll tell you if you pick a pipe size like 1-inch copper, for example, you're going to have to get about 5 or 6 gallons per minute to get that velocity up to where you're going to be able to, flush out the sludge that's in there, like this type of stuff here, and make sure you get a good clean out. So he said, that's what we do that most mechanical contractors can't do. He said, we've got a big enough pump, like this type of stuff here, that we can, he said, I think they can flow up to 24-inch diameter pipes now. They got a big trailer that's got 2 Cummins diesel-powered pumps that they just hook onto the system. He said, we just put an ultrasonic meter on that pipe. He said, we measure the size of that pipe, and we know how many gallons per minute we got to flow through that on the ultrasonic meter to get that fluid velocity up to, that 5 feet per second. He said, right at that number, he says, when crap will start coming out of the purge cart, out of the purge ports on it. So, if you're going to flush a system, either you're going to have to get a big enough pump, like a, pool pump or something like that, that can move 20, 30 gallons per minute, or break it down to really small loops, like, 1 PEX loop at a time that you can get, 3 or 4 gallons per minute through with a, with a 1/2-inch garden hose or something like that. So
I used a fire truck to purge a geothermal well up in Brighton Bush, up in Oregon.
Yeah.
Talk about cojones. Had a 350 horsepower pump.
Well, and I think up in Collins' neck of the woods up there, I met some loopers. I did a seminar up in Iowa, Nebraska, and up in that neck of the wood in the Dakotas. And up there they call them loopers. And loopers are guys, they're typically well drillers, but they put in either the well, they'll excavate if they have excavators, and they put the loop and manifold it and test it and fill it, and then turn it over to the mechanical contractor. And so the loopers buy old fire trucks to use as their purging cars. They said, we can haul the water out with us. We got plenty of pump on that, and they're cheap. You can buy them surplus, from the government or when a fire department upgrades. So he said that's how the loopers fill up the systems and make sure they've got them purged out. So when they turn it over to the heat pump guy that's going to connect to it, it's ready to go. It's been flushed out and filled, and they've got all the dirt and crap purged out of it. So yeah, that's not a bad way to go. So to make a long story long, anybody got any ideas or questions or comments or thoughts on what we've talked about?
Well, the only question that we had was the one that came from Harvey.
Yeah.
Advance these slides a little bit further forward here to get to the end. I guess we can ask that question again. Does anybody have any questions that they would like us to address at this point in time? Not seeing any.
For tuning in.
Bob's contact information is bob.rohr@caleffi.com. Excellent company, very supportive of everything that we do in the RPA. In fact, we just recently put together the ASSE 19210 standard, and thankfully for Bob and all of the hydronics books, is full of the hydronics graphics. It was a lifesaver in getting this whole program put together, so we appreciate what it is that
thanks.
your folks do for us.
No sense reinventing the wheel when it comes to doing those CAD drawings. You can spend hours making one drawing, so you might as well reuse what we did. Now, I will say not this month, but next month, I think it is, Mark Olson, our general manager at Caleffi, is going to do another water quality seminar. He wants to drill down into a little bit more because we're learning stuff. The more we talk to people and get the units out there and hearing, how they're using them, what they're doing. So he's going to drill down a little bit deeper than Siggy did on the first one, which was just basically that hydronics issue. But Mark's got more data and more stuff that we've learned since we've been out there doing this now for about 6 months. So.
Well, make sure they send a copy of that to us, and we will echo it to all of our email account holders so that we can make sure that we get as much attendance for you as we possibly can. These are important issues that a lot of people ignore. They think it's a set it and forget it type of world, and it used to be with the older, thicker cast iron components, but the stuff that we're dealing with today, if you're not paying attention to this, it's going to come back and bite you in the butt.
Well, it's not a matter of if it's going to happen; it's a matter of when. I mean, you don't want to have that conversation, 5 years or 10 years from now. I mean, just a couple steps. Now, I know it's going to add time and money to the job. It's going to take another trip back there to run a cleaner in there and come back the next day and flush it out. So, if you're bidding against other guys that aren't doing it, you're going to have to sell it to the customer and say, listen, if you change the oil in your car, do you put a new filter in or do you put the old filter back in? Say, if you're not putting good water in your system, the other guy isn't giving you a boiler with a warranty. He's just giving you a boiler. So, I'm not a used car salesman that I keep my foot in the door and pressure somebody, but you got to explain that to them that, it says right here on page 75 of your manual that the water has to be this, this, and this, and your water isn't. So that's why I do this extra step, and it costs you, extra money for me to do it, because I'm going to make sure that you've got, warranty protection on your pumps and on your boilers and on your all your components in your system. So
Harvey made a good comment that it's coming to the point where we have to handle water with cleanliness similar to that of refrigeration systems, and that's.
Well, yeah, that's an excellent analogy, because I knew hacks that I worked with when I was in the HVAC industry that would never put a new dryer on when they put when they changed the system because they're changing it, trying to save a few bucks. So there's a classic example. You put a new compressor in and use the old dryer. I mean, but that's what you're going to find out there is people just don't, take care of the fine details that makes it, right, or makes it the best way to do it. So.
Well, our next person up is going to be Kurt Nagas with Axiom, and he's going to come in and talk to us about their reservoir fill system that they produce that personally I think should be mandatory under the code. There's really no place in any one of the codes that I've read, and trust me, I've read every code in North America, that requires a quote-unquote make-up connection to a heating system. And when I was in the contracting business with my former partner, Tom Olds, we developed a device that was basically 2 expansion tanks. One of them was pressurized to seat pressure and had a pressure reducing valve between it and then the actual expansion tank for the system with the necessary backflow prevention, etc. And when we would fill up a system, we top it off, get all the air out of it, and then use this device. And we called it a PIG because it was originally developed for use with glycol systems, where we don't put a makeup at all. And as long as you didn't have any leaks in the system, then it wasn't an issue. And I think that a lot of the issues that we're having in the field as it pertains to boiler failures are probably related to a leak in the system. And that leak in the system is probably the relief valve pump that's pumping towards the point of no pressure change, and the pressure reducing valve is on the suction side of that pump, and every time the pump turns on, drops pressure enough to the point where it draws in a little bit of fresh water. You hit that relief valve threshold, it dumps, and then you start the whole vicious cycle over again. No leak is a good leak on any heating system. And Kurt has this pressurized system that the folks at Axiom have had out for a long time. And we're actually going to try to make a move with the Uniform Mechanical Code to see if we can get this instituted for sure where it pertains to systems that have antifreeze in them. Attempted to do that last year and basically got the technical committee's attention, but there wasn't enough time to dig into the real deep parts of it to explain to them why it was important that these systems be set up that way. But in any case, Kurt will be our next person up to bat. Should be an interesting show. Keep your eye out in your emails for notifications about the URL and the passwords on that. And lastly, here is our one and only advertisement. If you're not a member of the RPA, by all means, join this very worthwhile organization. It's of the members, by the members, for the members. Bob is a member. Bob's company is a member. It's a great bunch of people, been around for a long time, and we're not afraid to share information and would love to have anybody that sees this that's not a member join the organization. So with that, Bob, have you got anything else to say?
No, I'm good. Thanks.
All right. Well, thank you again very much, and thank your bosses over there at Caleffi for allowing you to help us out. And we'll talk to you in the very near future.
All right. See ya.
All right. Take care.